So energy is measured in joules. Joules are basically the force of 1 Newton applied over a distance of 1 meter. So that's basically a Newton over a meter. Write that. Because I'm sure there's going to be one question that asks you that. Or it's also going to be mass or kilograms. Let's do it like this. We'll make it generic. Force over distance. And then mass per velocity squared. Okay, so then the units are going to be joules in terms of units. We should say energy. So energy is equal to force over distance, which is also equals to meters, velocity squared. So our units are going to be joules. 1 joule is basically going to be equal to 1 kilogram meters squared over seconds. Okay, so which is shown right here. So joules are basically SI units, right? So that's the units that we commonly use in science for energy. So often we will use that, although you will see the other one, which was force, Newton, 1 Newton, which is a capital N over meters, is the other way. Okay? You'll see that sometimes too. Okay? Questions, concerns? Anybody want to give me money now?
What chapter is this?
Chapter 10.
Oh.
Last part. It's the last part of chapter 10. We're putting everything into play now. We're putting energy. So you remember when we talked about, when I showed you that equation where we had sugar being broken down to carbon dioxide and water? And then I said, you also get heat. And I said, oh, we're going to talk about this later, right? I showed you this at the very beginning. Now we're finally talking about it. What was that?
I remember that.
You remember that? Good. Okay, so another form of energy is calories, or another unit of energy is calories. So this is the one that we use in the US. We're notorious for using other forms. Now, the way that we define a calorie is basically, it's the energy required to raise the temperature of 1 gram of water 1 degree Celsius. Okay, so it's just the energy or the heat that's needed to go from 1 degree Celsius. Or it could also be 1 degree Kelvin, because we know that Kelvin and Celsius are the same in terms of when we take the difference between the two, right? Because we're just adding 270 what? What is that number to change Celsius to Kelvin? Hey, obviously I have to put that on the exam, huh? Are you there?
You kind of cut out on my end. You kind of cut out on my end.
Okay. What is the conversion for changing Celsius to Kelvin? We add what?
Isn't it like 232 something?
Is it like 273?
73.15?
15.
That's correct. 273.15. That is correct. Yes. So since we're adding that, you know, so if you just basically all you're doing is adding another degree to it, and that'll be your difference. So it's the same concept. So if you're changing a degree Kelvin or a degree Celsius, it's just that 1 degree change for 1 gram of water. Okay, so that's what a calorie is going to be equal to. The energy that it takes to get that 1 degree change. Okay, so 1 calorie is equal to 4.184 joules. Okay, or we could say that 4.184 joules per calorie. Okay, we get that nice little conversion going on there. Okay, so a kilojoule is basically going to equal, I should say 1 kilocalorie is going to equal 4.18 kilojoules. And that makes sense because a kilojoule, what does kilo mean? Like a kiloman. Kilo. Anyone? Kilo.
Is it
Thousand.
1,000?
1,000, yes.
1,000 per joule?
That's right. So if I have 1,000 joules and I have 1,000 calories, so I put 1,000 over 1,000, you're going to get the same conversion, right? So we're going to get 1 kilocalorie is going to be equal to 4.184 joules. 1 calorie is going to equal the same. So you're going to basically get the same type of conversion because you have 1,000 over 1,000. The thousands are going to cancel out, and you're going to get the same equivalency. And so you're going to say 4.184 kilojoules is equal to a kilocalorie because we have kilo over kilo. So if I had meal calorie and a millijoule, what is going to be the conversion?
Million?
What's going to be what? So how many millicalories? So if I have 1 millicalorie, oops, not calorie. And that's an M. I know it's a funny looking M. How many millijoules is that going to equal?
$4.184.
That is correct. Who was that?
Me, Sanhana.
Excellent. Good job, Sanwana. You get a brownie.
Oh, I love brownies.
Me too. So we just need somebody to make it now. Okay, so we know that if we have those conversions that have the same prefix on both tops and bottom, that conversion is going to be equal to what it normally is, right? So it's always going to be that 4.184 if we're talking about joules to calories or millijoules per millicalories, or if we were talking about centijoules per centicalories, okay? Piece of cake?
Yeah.
Or piece of brownie? Okay, who hasn't made a box cake? I thought, was it Ryan said that he's never made a box cake? We'll have him make a box brownie.
Oh, I'll pass it on to my mom.
No, we
She
want
makes
you to
good
make
brownies.
it. Your mom make good brownies?
Yes.
Okay, so we have one more conversion. Now this is a crazy one because have you guys looked at the back of your boxes? Like your food boxes, your brownie box?
Yes.
Mm-hmm.
Get the ingredients?
And yeah, you look at the ingredients, but it tells you all the calories in there, right? It tells you how many calories you're eating and everything, right?
Right.
Okay, so what was that?
I prefer not to look at it.
I know, me neither.
Just eat it. Live your life, YOLO.
Because I know exactly where it's going at the end of the day. It's going to my gut and my butt.
Oh my god.
Okay, so a food calorie, which is a capital C calorie, see that capital C? That's actually different than our lowercase c calorie, okay? So, but it's also, it means energy. So, but a food calorie is going to be equal to 1 kilocalorie, right? So this is the calorie that we use in chemistry, the lowercase c, but the one that they use in the food industry is an uppercase c, okay? And you want to distinguish between that. So you want to be able to sit there and say, oh, this is uppercase C calorie, right? So 1 calorie, food calorie, is equal to 1 calorie. Or it's equal to 1,000 small c calorie. So now you see why the US is a little crazy, right?
Yep.
Not only do we like to use the imperial system for measuring stuff, right? We start using capitals and lowers to distinguish between thousands of units, right? It's crazy. It's cray-cray. Okay? So, but you need to know it because that's unfortunately how the world works, right? I didn't pick it. I would change it if I could, believe me. Okay. It's kind of like how we have so many different ways of saying words, you know, instead of using one word, you know, we have like 50 different ways of saying it. Oh, if I want to be really nice to a person, if I respect the person, if I hate the person, you know, we all have different words for everything, right?
Caramel or caramel?
Caramel or caramel. Well, see, that's different pronunciation. That's a little different. I'm talking about like, let's see, like you piss me off, right? Oh, you make me mad. You make me upset. You make me angry, right? So depending on who you're talking to, right? Are you going to tell your boss, you pissed me off? I might, but I don't know too many people who would, right? Most people are saying, I'm a little upset about what you said, or, you know, something along those lines, right? So there's 5 different words to say exactly the same thing. So depending on who I'm talking to, like if I'm talking to my girlfriend, I don't tell her, you pissed me off, but I'm not going to tell my boss, you pissed me off, right? Okay, so it's kind of like that. So that's what these different units kind of represent, right? Okay, now knowing that, are you guys ready to play with them?
Sure, why not?
Well, it don't matter. You don't have a choice. So let's get started, and then you can hate me later. Okay, so this is what we have. Calculate the number of kilocalories, calories, and joules in 42.5 kilojoules.
Alrighty.
Okay, so this is what we're going to do. I'm going to give, who's going to volunteer? Who's going to do the kilocalories? Okay, Ryan.
All right.
Okay, who's going to do calories? Okay, Karina. I see you're volunteering. You guys are so great. Look at them. They're just so excited to volunteer. I am just trying to control, you know, their excitement. And let's see, who's going to do joules? Oh, my girl is here. Nancy.
Hey, what's up?
Not much. You're going to change joules. You're going to do joules for me, right? Because you're my joule. Nancy, you're my jewel.
Oh, thank you.
You guys don't tell Ro, okay?
He's right there, I'm pretty sure.
It's okay, she left me, so.
Don't tell everyone. Jeez.
We broke up. My heart is broken, so.
You didn't break the thermometer, did you? It's a brand new thermometer. Well, it's not brand new, but it's a functioning thermometer.
No, I didn't break it. I'm not that vindictive.
Okay, good. Okay, it's okay that you guys broke up then.
I'm hurt, but I'll get past it.
Bro, you just hung up the phone with me. What are you talking about?
Yo.
Can I annotate your screen? Is that okay?
That would be great. So this weekend, Stephanie's family fed me so much, I had to get rolled out the door. It was insane.
Went to visit her?
Yeah.
Yeah, he visited me.
Wow.
So deal with that.
Wow, I thought it was your jewel.
You
Yeah.
are. I would have visited you, but Roll told me, he was like, that's mine. You stay away. I know you, you know. So I was like, okay, you know. I'm not like water. I'm not a home wrecker.
He's not a carbon. He's not a hoe.
Man, I wonder if people start actually listening to some of the conversations we have in this class. Boy, I may not have a job tomorrow.
Yeah.
Your boss watch these?
Ooh, obviously they don't.
So if you don't, you know why?
What was that?
If you don't log on one of these days and we're waiting for you, we know why.
Exactly.
And this is on the chart table? Or are we supposed to know how to do this?
You're supposed to know how to do it. It's just unit conversions. And I just gave you the conversions on the slide before.
She just came. That's why.
Oh, okay. I'll flip back for you.
Hold on.
Teach you to come late.
Yeah, I was late. It was Rose's fault.
I know. He was distracting you. Okay, so these are your conversions. You see them? Take a picture so it can go back to that blank screen.
Yeah.
And we'll move this top one here. Oh. Oops. Sorry, Ryan.
You're good.
I still missed one. You got?
Let me check this screen.
Okay, you got it?
Yes, I got it.
Okay, Ryan. That looks beautiful.
I need help with mine.
Is that Karina?
Yeah.
Where are you going to start?
So 1 cal equals 4.184
But are
joules.
we going to start there?
Start
What's
with,
our given?
I don't know.
Start with what you're given.
So 42.5 kilojoules.
Okay,
Yeah.
so go ahead, write that down.
I'll try to write it on my phone, but it's going to be big.
If you tap the corner, oh, that's right. It's okay if it's big.
I can't get on my computer because my Wi-Fi is not working, so I'm using my network on my phone.
Oh, no, that's fine. But if you push your corner, oh, there you go. You got it.
See, it's huge.
Okay, that's all right. We can see it.
Dang.
You
You
have to
work?
shift it a little bit, you know. And I'll slide it over for you. Put your units. Okay. Okay.
Okay.
So, and the units are kilojoules.
Right. That's a KJ, sorry.
Okay. It's all right. It's all right.
I really apologize. It's hard to write it on the phone.
It's okay. It's okay.
Okay, I don't know. I don't know what to do
Put your
now.
KJ for you. Don't worry. I'll fix it for you. Okay. So
Thank
we
you.
have, and I'll write it almost as big as you wrote it. Oops, wrong color.
Okay.
Okay, KJ.
Okay.
Okay, so what am I going to do now?
So
I always like drawing my lines so that I know what I want to try to get rid of. And
so do this.
okay. So we have kilojoules. How can we get to calories? Can we steal anything from Ryan?
Don't
It
still
would be this. It would be the same thing, right?
Yeah. Only thing it's calories. Okay. So we
Exactly.
start off with, but you have one more step than he does, right? because you want calories and he has kilocalories. So then you're going to have to go from kilocalories to calories. So let's go ahead and follow Ryan's lead. Okay.
You might have to shrink that, but I don't know.
Let me see if I can shrink it. I'll try. I think I can.
Okay.
We'll find out here in a second. Oh,
Oh, yep. Yay. Okay.
okay.
And then I would do this would be there's 1,000 calories in a kcal.
Okay. So
and then these would cross out, right?
mm-hmm.
And then I can't see the front part. It was 4.25.
Yep.
So then you do
4.25.
4.25
Yep.
times 1,000 divided by 4.184.
That is correct.
Okay. Four point 184. I'm getting 10,157.7438.
Okay. So how many sig figs do you have?
Alrighty.
3.
3 sig figs. Okay. So let's go ahead and write down the number that you have, and then we'll change it to sig figs. I'm going to fix your calorie. I won't put a C there.
Okay.
Calorie, so that it's not looking.
10, 4.
And I'll try to put in the same color that you used.
10, 157.
It's 2 to 4 p.m. or 12 to 2?
Okay, if we want 3 sig figs, what is going to be our answer? This is going to be our determinant.
So 102?
Is it going to be 102?
Oh, no. Done.
Is that 102?
There you go.
So it's 10,000.
10,200.
That is correct.
Sorry, that was so big.
Okay. That's all right. Nancy got plenty of room. Now, Nancy, you're going from joules. You're going from kilojoules to joules.
Wait, what?
You're going from kilojoules to joules. Kilo. Kilo means what?
I don't know. Hold on.
Well, at least I know you guys are not drug addicts.
1,000.
1,000. Well, maybe one of you guys are. Who was that?
I said cocaine, but my mic was paused.
Wait, what? So
So 1 kilojoule is going to be equal to how many joules?
oh, I don't know. Do we have that?
You should know that. Kilo is a prefix. You've seen those prefixes. Like mil equals how many joules? 1 joule equals how many millijoules? Mil?
1,000?
What does mil means in Spanish? What was that?
1,000.
1,000, right? So
Yeah.
1,000 millijoules equal 1 joule. 1,000 joules equals 1 kilojoule. So those are just your prefixes that you got to remember, stuff that we did in the beginning.
Okay.
Remember I told you it's coming back with the vengeance.
Kilojoule. So 1,000 joules equals 1 kilojoule?
That is correct.
Oh, okay. So then, okay. Let me. So.
So do you like do the same thing as like the previous one? You would
Dimensional analysis?
yeah.
Yeah, that's all this is dimension analysis.
No, but like so like this part, the second one that you did, all of this, you would use that, but afterwards you would add another one, and you would put 1 calorie is equals to 4.184 joules. Would you do that? So
Could I do what?
So like, let's say this is what I'm given, right?
Yep.
And what is that? That's 1 calorie is
Yep.
equal to.
No, that's 1 K joule.
Oh, that's 1 joule.
Yeah, that's KJ. Yes. 1
So
kilojoule. So
I
not
had
one. So you're talking about here?
Never mind. I thought it
Wait,
was
wait.
1 calorie.
Oh, next to it?
Yeah, I thought.
Yeah, no. You're right. It's K-calorie right there.
Oh, so it's not kilojoule?
This here is K-calorie.
Okay.
This down here is kilojoule.
Kilojoule, yeah.
Yeah.
So, and then for each 1 calorie, you get 1,000 calories, right?
Yep.
So now with that, like, you could create another one to find joules, right?
Yeah, you could if you wanted to. I mean, or you could have just gone, since you knew that kilojoules, 1 kilojoule is the same thing as 1,000 joules, then just go directly that way.
Yeah, I was going to do it the long way. I got the same long way.
So you just wanted to do it the long way, huh? Is that what you're telling me?
Yeah, I just followed them and then just kept adding to it till I got back to joules.
Okay.
So, I mean, it's the same answer, but this is better.
Quicker, yes. Yeah, think about that time test, all right?
Don't start stressing us yet.
I'm not stressing you. I'm just telling you the truth.
Girl, I've been stressed. What are you talking about?
I forgot for like a little bit.
Pick up stress.
Okay, piece of cake. So this is just a dimensional analysis using energy. Not too hard, right?
Nah.
Okay.
I did something wrong. Because I did it the long way, right?
Uh-huh.
And I'm not getting the same answer.
So
How'd
here,
you set it up?
So 42.5 times 1,000 times 4.184 divided by 4.184.
So if you did it the long way, yeah, it would just be right here. You would add 1 cal on the bottom, and then on top would be 4.184 joules on top.
Mm-hmm.
Oh, yeah.
Yeah, and then so you multiply it all together, and then you divide, and you should get the same answer.
So this is going to cancel out, right? This is going to cancel out. This is going to cancel out. And so all you're going to be left with is just 4.5 times 1,000. I mean, 42.5 times 1,000. That's it.
Okay, I put it in the calculator wrong the first time.
Yeah, that typically happens. I'm not saying just you. That typically happens to a lot of people. Okay, piece of cake?
Yep. So what did you feed him, Stephanie?
Well, my mom made the food. I didn't.
It was a lot of food. Oh my gosh. I hadn't had so much food, and I had flan. Man, I was like literally rolling out of the house. Delicious. The lentils and what is it called? Cactus? It's
Nopales?
Oh, nopales?
Yes. Delicious. It was so good.
You like nopales?
Oh, I love it. Yes.
I don't like nopales.
So you sat there and had dinner, Dr. Henry?
What was that?
So you sat with her and had dinner?
I had lunch.
It was like lunch, huh? Yeah.
Yeah, it was lunch.
How nice.
I want dinner or lunch.
It was brunch, actually.
Oh.
Brunch.
Yeah.
They have mimosas, y'all.
What is
And I talked to her whole family, you know. I just realized that I knew her whole family, you know. I didn't just realize it. Of course, you guys know I know her sister because I call her sister all the time. So.
It's funny because Nancy thought that was my middle name.
Okay, can I move on?
Yes.
Yeah.
Okay. Tiffany says, hurry up. I'm going to fall asleep on you guys. Okay. So now we get to talk about thermochemistry. Now that you guys have an understanding of the energy and the units for energy that we're going to be using, the way that we define energy, we basically define it as heat, right? Action. And it gets, this is a good example. I was boiling water today, and I touched the pot. So hot, you know, a hot pot burns, right?
Mm-hmm. Yeah.
I felt like a little kid all over again. Right? So that gives off heat. So a lot of times chemical reactions will give off heat or take in heat. Okay? And we've talked about this at the very beginning. And I know you guys remember because we're talking about, is it endothermic? Is it exothermic? And you guys are like, oh yeah, I got this, right? Now we get to actually apply it. And now we get to put some numbers, right? Because that's part of chemistry. Okay? So chemical reactions are going to either give off heat or they're going to absorb heat. Okay? So when they give off heat, right, or they expel heat or they release heat, is that endothermic or exothermic? See if you guys remember.
Exothermic.
Exothermic, that is correct. Okay, so if it takes in heat or absorb heat, then it's
endothermic.
Okay, so the term that we use for heat, right, or we'll often say the heat of the reaction or the enthalpy of the reaction. Right? And we kind of define this as change, the change in heat. This change of the temperature, the way it started, to the temperature of the way it kind of ends, is the change in heat or the change in enthalpy. We define this as delta H. So enthalpy of a reaction is called delta H. Okay? You got that?
Yeah, hold on.
Okay. And we make it we represent it as the change in heat or the change in energy. So that's what that is. It's actually energy, because heat is energy. Okay? So this is basically just telling you everything that we just talked about. Enthalpy, what enthalpy is. So the H is just a symbol for enthalpy. The delta means change. And then the subscript R means for the reactions. So there's a lot of different types of heat. So there's the heat of formation. That's when you're trying to form a chemical, right? There's the heat of decomposition, right? When you're breaking down chemicals. There's the heat of sublimation, right? That's going from a gas to a solid to a gas. There's the heat of evaporation, right? That's the process of evaporation, okay? So there's energy that's associated with all of these different steps. And so we kind of keep track of that energy. So you guys are at that point where we're learning how to keep track of that energy, okay? So do you guys remember when I talked to you guys about sugar being the devil?
Can you say that again?
Do you guys remember when I talked to you guys about sugar being the devil?
The devil?
Is my internet bad today?
I've never heard that. I never heard you say that.
You never heard me say that?
No.
No.
Sugar being the devil?
Maybe you
Energy.
did in morning class.
Sugar being the devil, not energy.
Mm-hmm.
C6, H12, O6. You don't remember anything about that?
No, not really.
Okay, let me keep going. Plus O2. What am I going to produce? What type of reaction is this?
When they combine together? Is that what you're talking about?
Nope, it's not a combination reaction. Nope.
No.
Is it a combustion?
It's a combustion reaction. What are going to be my
What?
products?
Dang. I got
What's
it.
a combustion reaction, bro?
I think Dr. Henry wants to move on. I think.
So what are the products of a combustion reaction?
Water?
Water and is it fire and water? Or wait, no. Carbon and
Carbon what?
Ox.
It does have an ox, but not one.
dioxide.
Carbon dioxide. That is correct.
Dang, Nancy,
What
you see me?
It's also what you breathe out, right? So when you eat, you breathe in what?
Oxygen.
And then what do you breathe out?
Carbon dioxide.
CO2.
CO2, and you got to go pee, right? After having a really big meal.
Mm-hmm.
Pee or poop, one or the other. Sometimes both. Okay? So, balance this equation for me. You guys see the equation?
Mm-hmm.
Yeah.
You want me to move it up?
Yes, please.
Move it up. That you don't remember. Trying to make me work hard. Okay, balance the equation for me. Okay, who was doing that? Somebody started it. I saw Cho. Come on.
Oh, we're working on it.
Oh, you could put a 6.
6 where?
On the reactant side, carbon.
Product.
Wait. Yeah.
Okay, wait. You guys have to work with me. Go slow. I'm special. So.
A 6 on the product.
Wait, what's a
CO2?
On both of the products.
On the CO2. Okay, 6 there. 6 there.
And then a 6 in front of the O2.
Oh! 666. Sugar's the devil.
Oh, okay.
Okay.
That's Lucifer. Lucy.
Okay, so I have to remind you, huh? Okay, now that we have this chemical equation balanced, I also told you that after you eat a big meal, you also sweat. Remember me telling you that?
Yes.
Remember I told you my Thanksgiving story? Where I had to unbuckle my belt a little bit and I'm sweating and remember that?
You never told us that story.
I did tell you this story.
You never told us.
I don't remember the story. I think you're telling.
I told it to
He's probably telling the morning people.
Yeah, that's exactly what he's doing.
I told the morning class and I told you guys too.
No, you didn't.
Yes, I did.
I don't remember the Thanksgiving
You
story.
like them better.
And this is my first time seeing the sugar.
I already told you that, Nancy. But you're my jewel, though. You know, they're my diamonds.
You said you like them better? What's that?
When did I say that? I say that all the time.
Wow.
And then I tell them I like you guys better. So it works out perfect. Okay, so we also have heat, right? Because we sweat after a big meal, you know? And that's just your body actually doing combustion, a combustion reaction, right? It's almost fire. But don't boom.
So you're saying like, so I got a question.
Yes, sir.
So when they do those when they do those food eating contests, basically their body can overheat, right?
That's right.
Okay.
And that's why they get to that point where they're starting to vomit and all that stuff.
Okay.
Okay. Okay. So is this an endothermic reaction or is this an exothermic reaction?
Exothermic.
Exothermic. Yeah, it's an exothermic because we're putting it on the other side of the equation. Now, when we write this, there's a couple of ways that we can write this, right? This equation. We can write it as, here we can actually put a value for the enthalpy, right? So we can say plus that value, and it'll be a positive number on this side, on the product side. Or if it's an endothermic reaction, it's going to be a positive number on the reactant side, because you're putting it into the because you're putting it into the reaction. Okay, so when we look at those numbers, the delta H, the overall delta H is going to be equal to a positive number if we're putting energy into the reaction, and is going to be equal to a negative number if we're taking energy out of the reaction or energy is being released. You guys understand that? That's all right. Let me show you. All right, let me show you. Okay. Okay, so we have a combustion reaction with ethane, right? It's already balanced for you, so you don't have to do all of the hard work, right? So we have two ways of writing it. The first way of writing it is saying this chemical reactions, 2 moles of ethane plus 7 moles of oxygen gas yields 4 moles of carbon dioxide gas plus 6 moles of water, right? And then the energy per mole, and this is actually should be, I need to fix this slide, per mole would be negative 2855. Actually, for 2 moles in this case. They tell us 2 moles. Okay? So this would be one way of writing it, the way we have in here. And this is kind of like saying, here's the chemical reaction, but here's the enthalpy. So I'm not going to keep it all in the same equation, right? The other one says that here, this is the chemical reaction and the enthalpy all in one equation because we put that plus there. So that means that we're releasing this amount of heat for this reaction. You guys understand?
So is it like the same concept of what you put in is what you get out?
Exactly. Remember? So what you get in is what you get out. So the thing is that we're putting in these chemicals. The bonds here are being broken, right? Those breaking of those bonds, that's being taken care of by that energy that's being released. Okay? Because we broke so many bonds, we were able to release that energy. So these carbon bonds are storing energy in them, right? That are here between this molecule. As soon as we break those carbon bonds, then this is the energy that we're able to get from them. So by us burning ethane, we're able to get that energy. And so we're keeping track of it. Do you understand?
Yeah.
Okay. So when we look at the decomposition of ammonia into its elements, that's an endothermic reaction, right? So we have the choice. We can write it like this, where we have 2 moles of ammonia plus 92 kilograms of heat is going to equal ammonia gas and 3 moles of hydrogen gas. Okay? So basically, we have to put energy in for us to break those bonds so that we can get these products. Okay? So that there's an endothermic reaction, and that's how we show that we're putting energy in. That's one way. The other way of showing that we're putting energy in is that we use a plus 92 over here. And this is kind of like just putting a semicolon. Is that right?
I think so.
Okay, so it's like putting a semicolon here and saying, this is the enthalpy that's going to be associated with it. We're still keeping track of the energy, right? But we're not putting it in the equation itself. You see the difference?
Yes.
Okay.
So
Okay.
it's the same thing, it's just 2 different ways of writing it?
That's right. And you will see it. You will actually see it written both ways. Although this is more prevalent, you'll see this more often, because typically what you'll do, you're keeping a running tally of all of the different energies from all of the different reactions that are going on. So sometimes you'll be doing a reaction, one thing makes one thing, this thing makes another thing, this thing makes another thing to get to a final reaction. So you're going to keep a running total. Okay, so it's a lot easier for us to do it this way, right? So then that way we can keep the energy separate, but we keep track of the equations independent. Okay, questions, concerns, Cash? Cockroaches. Or should we say brownies?
None.
No cockroaches.
Candy.
Candy.
Thermometers.
Thermometers. Okay, so you guys want to try this out?
Sure, why not?
Excellent. I like your enthusiasm. Let's see.
There's no
Okay,
cap.
so we're gonna have, let's see. Who am I gonna pick on? Tiffany, are you there?
Yeah.
And Stephanie, are you there?
Yes.
Excellent. So Stephanie, I want you to write it as being part of the equation. And then Tiffany, I want you to write it as being outside of the equation. So all it is, I'll read the question. It says, the thermal decomposition of limestone solid calcium carbonate, CaCO3S, to lime solid COS and gaseous carbon dioxide is an endothermic reaction requiring 178 kilojoules per mole of calcium carbonate decomposed. Write the thermochemical equation in 2 forms. Okay, so Stephanie, you're going to put it into the reaction, including the reaction, and then Tiffany, you're going to do it as the side, on the side, like the running total.
Okay.
So what is the first thing that you want to do? Don't freak out, breathe. I know it's something new.
I'm gonna write like the whole equation first.
Okay, so write the chemical equation first.
What's limestone?
It tells you right there. It says lime, and it's solid calcium oxide.
Oh, okay.
It said, I'm sorry, limestone is solid calcium carbonate. Lime is solid calcium oxide.
Oh, okay.
Like actual lime?
What was that?
Like an actual lime?
Not the fruit lime, but the mineral lime. So
I
like
didn't even know it was a mineral.
yeah, there's a lime deposit. So it's like, well, it's calcium oxide. And you know, on your toilet, you know how like you get those water stains on your toilet? Are you there?
Yeah, like.
Okay. So that brown color stain, right, on the toilet, and you scrub and you scrub and you can't get it to come off.
Yeah.
That's lime. Because water has calcium carbonate in it. And so what happens is that the calcium carbonate over time, after it sits there for a while, the carbon dioxide will actually start bubbling out of it, or you'll get decomposition of it over time. It breaks up and you're left with the lime that's sitting on your toilet, and then you're left with carbon dioxide that's either going in the water or going in the air.
Oh. How do you get rid of that? Bleach?
You can react it. So there's this stuff called CLR, right? And it's basically, it is a component that actually breaks the calcium oxide back into an ionic form, and then it associates, so then you can dissolve it. Okay, so Stephanie, you got your equation written down?
I don't know.
Well, who? So is this you?
Yeah, that's me.
Okay. But you have one more part to add. What are you going to do? Which side are you going to put it on? That 178. Put the pressure on. Right or left? Reactant or product?
I'm going to put it on the
reactant.
I think Ryan's directing track or something.
Left.
He was singing a song. To the left,
It's on the, isn't it on the reactant because it's endo?
That is correct. It's on the reactant side because it's endo. That's right.
So in this case, the reactant is on the right side.
Okay.
On the left side.
Left side. To the left, to the left.
Because it's endo. You just said it, Nancy.
But, yeah, but isn't...
Read what it says. It's an endothermic reaction. So is it going to be on the product side or the reactant side?
Reactant side.
Yeah, I know it's on the reactant side, but I thought that that was a product because
no,
I thought the
it's not a
reactants
product.
were...
It's considered to be a reactant because you're putting it in the reaction, right? Because the reaction isn't going to happen unless you put this energy in.
No, like, I get that part. It just was confused of how it's written, I guess.
So what happened, Michelle? I was calling you everybody. Jennifer, Michelle. I'm going to call you Jonathan, Michael, you know.
No. That's funny. So I would put calcium carbonate, right? After this.
Yeah, it would be kilojoules of calcium carbonate. Yeah. So kilojoules per mole calcium carbonate. Yeah. Because so we can base it on any of the chemicals in the reaction, right? But we're basing it primarily on the one that we're most focused on, the most important. And so don't forget your plus, because the plus is essential for that part.
This would be the calcium carbonate already, this part.
Yeah, that's the calcium carbonate.
Oh, okay.
Yeah.
I thought I had to have like another one or something.
No, you don't have to write that. This is it. That's all you have to write right there. Okay. So, Tiffany, you get to do the other one. What would you do for the other one?
You're asking from me.
So I want you to write the other form of writing this chemical equation, this thermochemical equation. So when we're talking about thermochemicals, we have to take into the enthalpy, right? I'm going to slide this over. So you're going to have the same chemical equation.
We don't have to write that triangle thing?
No, that's what she has to write. That's what I want her to write.
I have no idea.
That triangle thing.
Yeah, I missed
The question is, with that triangle thingy, is it going to be positive or negative?
Oh.
Endothermic, positive or negative?
Negative.
Nope.
Positive.
So if you think of negative, negative means that it's being removed from the reaction. Negative, we're removing it. If we're putting it in there, we're adding it to the reaction. So it's going to be positive. You're going to write delta H R equals 178 kilojoules. Oops. I'll fix that in a second. Per 1 mole, or per mole.
So we would still.
Those are considered the two forms?
That is the two forms. Okay, so those are the two different ways that you can write a thermochemical reaction, right? If it's an endothermic reaction, this number is going to be positive all the time. If you write it this way, that's an R. What the fire? Let me fix my R. You can also write it this way. So this is one form up here, what Stephanie wrote in red. This is the other way of writing it. It means exactly the same thing. You understand?
When we write it the second way with the little change, little triangle thing, we still put it on that side.
Yeah, you normally put it. It's kind of like you're putting here. You're writing the chemical equation, and like I said, it's kind of like writing a semicolon and saying, "Oh, here's the heat that's associated."
Oh. Okay.
We as chemists, we get lazy, so we don't put the semicolon, right? And that's the truth, because in the early days, they actually used to put the semicolon. We don't now because we're hella lazy these days. So. Okay, questions?
So would it just say exothermic if it was? Is that how it's going to be
So,
written if it's negative?
Yeah, so it would say if it was exothermic, this value would be a negative value, right? And then it would be, it's also on the other side of the equation. So if this was exo, this guy would be on the product side because it's being released, right? So it's kind of like you're removing it from the equation, you know? It's being released, or the reaction.
Is that number always going to be given to us?
In most cases, it will be given to you, or you're going to have to calculate it. But you guys, right now, you don't have to calculate it. 1A, they have to calculate it. Okay, so it's going to be given to you in most cases. Okay? Questions, concerns? Cash?
Are we going to do another one?
Credit? We can do another one. If you want to, let me think of something real quick. Let's see. We'll do two. Okay. Your two questions. I'll put you in your groups. I'll give you, it'll take you what, 10 minutes?
Maybe.
5 minutes?
10.
Okay. Give you 10 minutes. Are you ready?
So she's gonna do the one with the triangle?
That's right.
Okay.
Should I just say it like that?
Honestly, yeah.
The triangle.
Okay, so let me
Triangle thingy.
triangle thingy here.
Two. That's awful. Okay, hopefully y'all can read that.
Mommy.
Yes.
Oops. Oh yeah, that's right. Yes. Yes, Alyssa, please. Please do. I'm just sitting here waiting and so if you write it in the chat and I'll put it in for you. So Tiffany, are you forgetting something? Or are you still working?
She said bye.
She said bye.
There she is.
Oh, I guess I should look to see who's there. Did we lose a few people?
Mm-hmm. There's 13 people.
Where are the two? Where's Veronica and Carissa?
I don't know.
I don't think they're here.
I'm gonna say I'm agree. They didn't jump ship though. That's good.
You can see her, Tiffany's boys' heads in the camera.
And where's Jamie?
Mm-hmm.
Sarah, are you there? Tiffany, is there more to the equation that we need to put on there than just the delta H?
Oh, I don't know. That's all I wrote down.
The equation that we wrote down, remember?
I guess I didn't finish writing it. Sorry, I'm like trying to coordinate with 3 kids and do this at the same time.
Just breathe.
No, I didn't.
You okay? Sarah, are you there? Did we lose her? Looks like we lost her.
I thought you said you loser. I'm like, that's not nice.
You loser. I think he's telling you to just breathe. He's like, really, no.
He has trouble with connections. So anybody want to take Sarah's place? Let's see.
That's the second one on the first.
Yep.
You can't. Let's see if I got me.
But we'll start with Jamila's. Jamila, so everything looks good except this here is 273 kilojoules per mole of water, right? And we have 2 moles of water.
Oh.
So in this case, we would have to double the amount that we have for there.
So what would you change it to?
So 236 times 237 times 2?
Yep. And then it'll be per 2 moles because it's based upon the water molecule.
Nancy, you said 237 times 2?
Yep.
Yeah.
Which is 574.
Let me do it. I'm not a genius.
474.
Excuse me. No, yeah, right, 474.
Yeah. I'm just telling you the right answer.
Yeah.
I'm confused.
Because this is based upon 1 mole, and we actually have 2 moles that are present.
Why are there 2 moles?
Because when we balance the chemical equation, there's 2 moles of water.
So I would put 474 K.
Yep. Technically, I guess you could still leave it as 273 per mole since you have it in per mole of water. I guess technically that would be correct, but normally because we have the equation based upon 2 moles of water rather than just 1 mole of water. So, but
You mean 237?
it's 237 times 2.
So you just here, I'll write it down just so they.
That's because there's like the coefficient is 2, right?
Yeah, because it's twice. We have twice the amount of water. So
What if the coefficients were different? Like, what if one was
if you took it a half, like you divide everything by 2, right, and you had a half of an oxygen, which is acceptable for these type of equations, just for that reason. So then that would be okay.
Okay.
So on the test, if we wrote it kJ per mole, would it be wrong? Like
If
we
you
wrote
wrote it kJ per mole, it would be okay. However, what you're going to write in this case, because you're saying I have 2 moles of these, right? So you just put kJ, and that means that you haven't divided it by what we're looking at. So normally we would put it in the interest of, let's see, how do I explain this? We have it relative to the water, right? So we'd set up our equation relative to the water, okay? So then when we write our equation, it would be 237. But you guys didn't know this, so I'm not holding it against you.
I didn't know that.
What was that?
Nothing.
Guys, stay out of my room. I keep turning on the light. Yes. Oh yeah.
Okay, so we would write it in this form where we actually have the half of reaction so that we can keep it in the 237 component.
Oh, I see.
You understand?
Yeah.
So, but if you're writing it with the 2 there, you're going to have to multiply it by 2.
I see.
Yeah.
Okay.
Okay, let's see. And that's the same thing here. Since we have 2 here, we're going to have to multiply this guy by 2. And then it would just be 2, what is it? Now it's what, 5, 7, 5, 4, or 5, right? We're at 5, 7, 5, 5, kJ. Okay, unless we divided everything by 2, and then we can use that value there, because this is per mole of butane. So we divide everything based upon 2 in that case.
Butane. Okay.
Yeah. Yeah. So this is one of those cases because you're trying to keep a running tally, right? And since we're keeping a running tally, then we want to always, since we're keeping a running tally, we always want to put it based upon what we're looking at specifically. So in this case, we're looking at butane, you know, per mole of butane, per mole of water. So we want to try to put that in so that it's only 1.
Okay.
Okay. Okay, so let me write down Alyssa's answer real quick. Sorry about that, Alyssa. I wasn't ignoring you completely.
So I just want to clarify real quick so I could write this on my notes. If you know it's a combustion reaction if it has carbon, hydrogen, and oxygen?
Any hydrocarbon or organic compound burning is going to be a combustion reactor. So anytime you see the word burning or oxidized or fire or fuel, you know it's going to be a combustion reaction. So that means you're always going to need water because fire doesn't burn without, I mean, not water. You're going to need oxygen, right? Because fire doesn't burn without oxygen.
So if it was something else, this equation would be a single replacement?
If it were something else, it would be a single replacement?
Like if it wasn't burning?
If it wasn't burning?
Yeah, like...
Even if it was burning, okay, so if it isn't burning, right, let's say it was there was no spark or anything to start the fire, right?
Mm-hmm.
You wouldn't have a reaction. It would be no reaction. You need that spark to get that fire started.
Oh, okay.
Okay? And believe me, a lot of times it don't take much to get that spark started. Which you'll probably find out from a lot of people. As they burnt down their house. Okay? So, okay, Alyssa, that's the equation. So you want to make sure that you balance it, and then you want to put it so that the chemical that you're looking at is only 1 mole. That's normally how you do it, okay? So if you balance it and you get it completely balanced, then the way that Jamila did it here would be fine, since she had it based upon 2, but she needed to multiply it by 2. The enthalpy, since it was kilojoules per mole. You understand?
So it has to be that way?
So it has to be, so it would be this way. What Jamila has written down here, that's going to be in the place of this. Okay? Or you could write it in this form here where it's only based upon 1 mole of water.
Okay. Oh, okay. So that would have been good as well.
Yeah, either way would be acceptable, right? This is the one that you're going to see 99.9% of the time. or I should say, what you're really going to see 99.9% of the time is the other form. So what Sarah was going to do when she got back. So which is
And the ones that she did right now, this one, that one's also good.
which one?
This one.
Down here?
Yeah, this one right here.
We don't have to multiply everything by 2?
Yeah, so in this case, you'd have to multiply it by 2 right here.
Oh, okay. The answer.
Yep. Oops, let's see. Oops.
Because of the coefficient in front of the C4. H10, right?
Yes. Yes.
Okay.
So we just didn't finish balancing that last one. So the way I was going to do it was to write it out like the way it is in the yellow, the 2CH4, blah, blah, blah. Okay. So the way Alyssa wrote it, would we be able to write it like that, like the balance equation, and then again, just double the 287? You know what I mean?
In this case, yeah. So you could have put 2, and then double that value.
It would have been 2 butane, and we got to double the.
Yeah. Yeah, you could have done that. But like I said, you'll see this more. You'll see that more frequently than you would see the version of the 2 times. Okay. Even though that your text kind of tells you just the 2 times. I'm just trying to prepare you for what you'll actually see in real life and in tables. So they like using the halves in tables. So, and this is delta H. Okay, piece of cake.
Kind of.
Okay, you guys ready to move on?
Yes.
Excellent. Okay, now you want to apply it, right? So you've learned how to write the equations. Now we want to actually apply it. Ready? Can I erase?
Yeah.
Everybody good?
Yeah.
Okay, so at the end of the day, or at the beginning of the day, I guess it really just depends. So we can also do the same thing that we've done with mass, what we've also done with moles. So we can do conversions using stoichiometry, right? So we can do the same thing in terms of energy, right? So and our enthalpy. So we can use the amount of energy that's being produced, or we can use the change in enthalpy for reaction to figure out the number of moles that are, and then we can use that to figure out the number of grams by using the molar mass. Okay. Do you guys see that? How it feeds into it? Here is your example. So what is mass of liquid in octane H18L, a component of gasoline, must be burnt to provide 9.05 times 10 to the 4th kilojoules of heat. your enthalpy of reaction is negative 5,471 kilojoules per mole of octane.
Okay.
So what are you going to do? What's the first thing you're going to do?
Identify our given and what is wanted.
Okay. So our given
is the 9.05 times 10 to the 4th kilojoules of heat.
Okay.
And then our wanted is the mass of liquid N octane CH or CaH18.
Okay.
So it doesn't say, like, we're looking for mass, but are we assuming it's grams in this instance?
Yeah, mass is always going to be in what units?
Grams.
Okay. So you're going to make the assumption it's grams. If they're not given to you, normally we use grams.
Okay. So are we going from kilojoule to mole?
Okay. But what would be the first thing that I'm going to do? What's happening here?
Something's being burned.
Something being burned. Okay, so then what is the first thing that I should do?
Combustion?
Write out the combustion.
Write out the combustion reaction.
Uh-huh.
Good job. Okay, what is the reaction?
Liquid and octane.
Okay, so what is that? C.
8H18.
Plus oxygen.
Okay, what's wrong with JD? Who drugged her?
Judy's going through a midlife crisis.
Just trying to be Andy.
Trying to be Andy? Okay. Don't be so mean there, Nancy.
No. Nancy, that's Karina.
Oh, Karina.
No, that wasn't. That was Nancy that said that.
That cracks me up.
Yeah, it was me.
Did he drop?
No, he's working on the.
Has he been in the morning?
He came in the morning.
I missed his whispering.
Yeah, he better not be dropping. He's in my music video group.
He's so funny.
Yeah. What are we going to produce?
That'd be CO2 and water, right?
Okay. Is it balanced?
No.
Nope.
No.
Oh my God.
10 minutes later, and she's still laughing.
Remember, burned his house down? That's hilarious.
Wait, he burned his house down?
No, he said he almost did because he was doing something with fire.
They're talking about him when he's not here.
Anyways.
Okay. Balanced. Come on.
No.
Oh, 8.
There's something about an 8. Where am I putting 8?
In front of the CO2.
Okay.
And then we put a 4 in front of the H2O.
I feel like these numbers are going to be high.
Oh, wait,
like
no,
really
not
high.
A 4.
No,
9.
you would bet 8.
9. What is 18?
Oh,
18, yeah.
9.
Okay, oxygens. How many oxygens are that? Is that? No.
16, 17.
That's 2, and then
2.
side it's
11, right?
16.
It's 8 times 2.
Oh,
16. Plus 9.
Plus 9.
25? Wait, I don't know. I can't do math this late at night.
16 plus
Yeah,
9
20.
is 25.
25.
Okay.
That sucks.
Oh crap. Do we need a
Fraction.
What's
I heard a fraction. So what is our fraction?
25 over 2.
Okay. Now here's the beauty of it, right?
Can
How
just
many
leave it
moles of the octane do we have?
more?
1. So we can actually leave our equation just as it is so that we can use this number just as it is.
So
Okay.
if it was 2 moles, I would have to multiply all of that by 2.
You'd have to multiply this whole number by 2, yes.
Oh, okay.
Okay? You guys understand?
I didn't know if you have 1 mole of octane.
What's in front of it?
Oh, got it.
So we're looking at that rate, the coefficient. Okay? So we can leave it in this form so that we can use this equation. Okay, so this is perfect, right? So as Ryan was saying, now we know we can start off with our given. What's our given again, Ryan?
the 9.05 times 10 to the 4th kilojoule of heat?
Okay. So let's start off with that.
We're gonna work dimensional analysis, correct?
Yes, sir.
So would it be times? What's the?
Can we use that that equation, that equivalency up there as an equivalence?
That's right.
Mm-hmm. So 1 mole of C8H18 will be at the top. And then we need to.
Do we keep it as a negative?
What was that?
Do we keep the negative in front of it?
Nope. Because the negative just tells us whether it's going to be on the product side or on the reactant side. So the value itself is going to be an absolute. So then we just use the value as it is. So we use
Okay.
5. So that means KJs are going to cancel out.
Mm-hmm.
And we want
grams.
Was telling us we want grams.
So this would be. We have to calculate, I believe, the molar mass of
C8H18.
Okay. So the molar mass of C8H18. So let's do it over here. So we have C. We have 8 of them. 8 times. What is the?
12.
Oh, that's good. I think somebody's
Plus
learning
18.
there.
Did I ask this already? Do you want decimals?
No, unless I absolutely must have them.
Okay.
Oh, here.
114.
Okay, so, and you said H is 18.
Mm-hmm.
Correct.
So this is 96 plus
18. 114.
114.
Okay.
Grams of C8H.
And then that will have the equivalency of equaling to 1 mole of C8H18, and that will cancel that equivalency out.
You guys are talking faster than I can write.
I was expecting Stephanie to go in with her little pin.
For what part?
Okay.
Then
What do you guys get?
1,885.
Oh, I wrote it in scientific notation.
The 1,800 and what?
And 86, I guess.
How many sig figs?
No, 3. So 1,008.
Wait, what?
No, 1,890.
Okay.
Wait, how is that happening?
Not scientific notation. What?
I'm not getting an exponent.
You're not getting what?
I'm not getting like exponents after.
He turned it into one.
Oh.
Yes.
Yeah.
I changed it into exponents. I'm a little slow. Piece of cake?
Yeah.
How did he change it into exponents?
What was that?
How did he change it into exponents?
Because it's 1,880, I think it was 86. Is that correct? Right?
Mm-hmm.
So then I know that that's 1, 2, 3. So then I go 1.89 times 10 to the 3 because I have to move it over 3 spots.
Oh, right.
Don't forget that. You guys act like you didn't take the first part of this class. You're like, oh, I just forget it.
You know how many weeks ago that was, Dr. Henry?
Yeah, but I told you that this is a cumulative thing, right? You're going to always see it.
So
it's going to come back.
It's hard to
Back and
remember
haunt you.
everything.
God, you act like you're 50 or
I
100.
feel like I am. I have a bad memory. Like, very.
They say if you stop smoking that marijuana, your memory gets better.
I've never smoked in my life.
Lies.
Somebody called her out there, says, lies.
I've been thinking about quitting.
I don't smoke. I've drank once and that's it.
Yeah, you're boring.
Okay, you guys ready? You want to give it a shot on your own?
Sure.
I guess.
Okay, so let me give you the problem. Let me pull it up real quick. So the morning class, don't say that I give you guys an advantage. I'm giving you the same question I gave them. So let's see. With the same typos and everything.
How's that an advantage?
Well, they say I give you guys an advantage because I give you guys a different problem.
Oh.
They tell me. Okay, so let me escape this. Hello. They say I love you guys more than I love them.
It's true.
You guys see that? So, is everybody back?
I think
I think you're missing one group.
Missing one group?
Yeah.
Okay. Let's see who's missing. Okay, so where are we going to start at? What is the very first thing that we want to do?
Identify the given.
Identify the given.
Mm-hmm.
It's really weird. Why do I have 3 windows? Oh, I guess I can do. Oh, I get it. Never mind. I know why I have 3 windows.
why?
Because one shows me all you guys, and I can put that on one screen, and then I can put the other Zoom window with you're showing what you're showing, and I can show what I'm showing.
So you have a multiple screen setup?
Yeah,
Really
and it's confusing the hell out of me, but that's all right. I'll get used to it. Something new. Okay, so
I always knew it because you would look somewhere else, and I'm like, screen is like.
it could be that I just didn't want to look at you, right?
Yeah, I guess you have.
No, I have multiple screens. Okay, so Nancy, so the very first thing that I want to do is what? You said identify my givens?
Yeah, Ryan said that, but I second it.
Okay, you second him. So what are my givens?
The length of the marathon.
Okay.
And the calories she's going to be burning per mile.
And, oops, let me erase that. So you'll be able to see what I'm writing here. So you said the length of the marathon.
Correct.
And then I have the equivalency here.
Uh-huh.
Okay. Per mile.
Correct.
Okay, what else do I have?
You also have...
We have the entropy. So it's a combustion, right?
Well, not because there's an enthalpy, but we know it's a combustion because we know our body does combustion, right? When we break down sugar, it's a combustion combustion reaction. So, but you're right, it is a combustion reaction. So what should I do in this case?
Do you add the O2?
Okay, so I'm going to add the O2. So are you telling me I should write the equation? Is that what you're saying?
Yes, write it down.
Okay, so what is my equation? What am I going to start off with?
The C12H22O11.
It says C12H22
and O11.
O11.
Plus O2.
That's a solid. Plus O2.
Yeah.
And that's going to yield.
Water.
Okay. Water.
And CO2.
And CO2.
See, we didn't do that.
Yeah, we forgot to do that.
That's the first thing that you should always do, right? The chemical equation.
Oh, Stephanie, we're wrong.
What's that?
Oh.
I said we're wrong. We didn't do that.
So is there still hope to get the problem right without that?
You can, but you're setting yourself up for failure if you don't write the chemical equation, a balanced chemical equation, because that's going to help you, right? Because right now, you're kind of given to what you want, right? And it kind of works out because of all the stuff you're given, but it just so happens to work out because of all the stuff you're given.
Ah.
So let's go. What are we going to do next?
Balance the equation.
Balance the equation. Show.
11 in front of the H.
You said 11?
Yeah.
Okay.
Would it be a 12 in front of the CO2?
Okay.
And that's 20.
It's 35. It'll be a 35.
35?
35 over 2 on the O2.
Okay. Okay. Okay, so what's next?
So do we calculate how many kilocalories or how many calories she's going to be burning throughout this marathon?
Okay, so how would I go about doing that?
Taking the length of the marathon, timesing it by 100, because that's the calorie per mile.
Okay, so let's do it in terms of our nice equation. What do I keep on doing? Oh, I have to remember, I can only write the length of your, so I have, you're saying 26.219 miles.
Mm-hmm.
I'm going to use MI for miles.
And then to 100. 100 calories per mile.
Okay, so 100. Capital C calories?
Lowercase.
No, capital.
Oh, yeah, because that's, yes.
And then 1 mile on the bottom.
Okay.
The answer you get should be lowercase c.
Okay. So then, what am I going to do?
Multiply that across.
Okay.
And you get...
Well, let's just make a long equation, because then it just cancel out units. So then that gives me calories, capital C calories.
Mm-hmm.
So then what do I want to do?
So,
because ultimately my goal is to get grams, right? So
correct.
At the end of the day, I want grams of sucrose.
So we go to
okay, that's my goal. So what is my next thing?
Would you need to put calories at the bottom and convert it to kilocalories?
Okay, so how many capital C calories will equal a
1,000.
1,000.
Are you sure?
One.
Well, 1,000. One capital CAL equals 1,000. No, isn't it 1 kilocalorie is equal to 1 calorie?
Okay.
It's 1 kilocalorie is equal to 1,000 calories.
Okay.
There we go.
Okay, so then that gives me kilocalories.
Correct. So
wait, what? Why is there only 1 cal on the bottom?
Because 1 capital C calorie is equal to 1 kilocalorie.
Oh, I didn't even know that was different.
So could we multiply this straight across and get the kilocalories?
Well, let's keep going. Come on, we're not going to waste our time doing that. So what is the next thing that we want?
The joules.
Okay.
Kilojoules.
Kilojoules. So what is the relationship between kilojoules and kilocalories?
1 kcal equals 4.184 kilojoules.
Okay.
Oh, I did this way longer.
As long as you got the right answer.
That's right. That's what I'm hoping for. I'm like, hopefully this answer is right because.
That's a point.
Kilojoules. And are you going to go to the heat one now? Right there?
Okay. The enthalpy?
Yeah, so on bottom, would you put the 2221.2 kilojoules per mole?
Okay.
And then, so on top, do we 1 mole?
Do you want to cancel the KCl in the bottom?
Yeah, I'll do that.
And then for moles, you go to gram?
Okay. And what is the molecular weight of C12H22?
342 grams.
Okay. Can you write how you did that in the corner of her, right up here?
Of course, Dr. Henry.
Up there?
Yeah.
Where that X is at?
Yep. Let me write that.
No, you can stay your ass there. Okay. Well, who did that? Mm-hmm.
Oh,
You said, who did what?
Tú también, okay?
Is she
You're giving me a
talking to someone
timeout?
else?
She's talking to someone else.
I get a timeout. Dang, I'm in trouble.
where would the like balancing the equation? Where would that come in place here?
So you always want to have your balanced equation because let's say I asked you about the oxygen, right? How much oxygen would she need to keep from passing out? Could you figure that out?
35 over 2. Oh, okay.
So you plug that into this equation right here at this point where you have moles of this guy to moles of that guy.
Oh, so instead of 1 mole of C12H22O11, I would have 1 mole of oxygen, and then
You would do, well, no, you would plug it into here.
where?
Right? At this point here. So if I asked you, so you do exactly everything else, but when you get your 1 mole of C12H22O11, you compare that to your moles of oxygen.
Mm-hmm.
So this exact same part here, right? But at this point here, you're going to use your molar-mole ratio. So you'd go 1 mole of C12
H22O11.
H22O11 over
35 over 2. Oh, 2.
moles of O2. And then that would give us moles of oxygen, or we'd go, if we wanted grams of oxygen, we just convert that to 1 mole of O2 to
32.
32, thank you, grams of O2.
That's if you were asking for oxygen, correct?
That is correct. In which I'm allowed to ask for anything I want to, right?
Yes.
You guys should be able to get it.
Please don't.
So usually I have a problem like this, and it'll be like a 2-parter or a 3-parter, where I'll ask for the first part, then I'll ask for the second part because, you know, there's a tendency of people not writing their equations.
So if you mess up the first part, you're going to mess up the second part and the third part.
Yep. You should always get in the habit. As soon as you have a chemical reaction, it talks about a reaction, it gives you the information to write the chemical equation. You want to write down the chemical equation. Right? and you guys know enough about combustion and us breathing and all of that, you should be able to write down the chemical equation.
So the answer is 1.6889 grams of table sugar?
There's a 0.1. So because it's 5 sig figs, 1, 2, 3, 4, 5. Why doesn't that point work out? It doesn't look up. It doesn't show. There you go. Yeah. So it's 1,689.1. grams of sucrose. Piece of cake?
Mm-hmm. When you explain it, yeah.
It's just following the trail, right? Okay, piece of cake, piece of cake. So we'll erase this part so nobody gets confused.
How come when you're balancing the equation on the reactant side, you didn't put down 11, 12, 13 oxygens, you just kept it at 2 oxygens?
No, because I can use this as my dividing number, right? So, and then I could have did the correction, right? Because then we know that we had 35 over here, 24 plus 11, 35. So then I know I can use 35 divided by 2. So I kind of use it to my advantage.
Okay, just to keep that sucrose the way it is. Okay.
Is that right? 35 over 2? Or did I screw up? No, we're wrong, actually. This is incorrect.
Because I did 35 over 13.
Yeah. So let's do it. So it's what? 35 minus 11 would be 24, so that would be 12. Is that correct? 24 plus 11.
I actually didn't even put the 12 in front of the O2 gas. I just added the 11 subscript with the 2 subscript on the reactant side. 11, 12, 13, and I just got 13. And I just did 13 over 15, or 35 over 13. That's just confusing me right there.
What is?
I know that I need to keep the sucrose as is.
Yep.
I'm just unsure.
So we have, this here is 11, right? So we have 35 oxygens over here. For it to be 35, for it to be balanced on both sides, then it needs to be, this has to be 24, right?
Right.
Plus 11 that you're getting from here.
Oh, okay.
Yeah.
So I don't even need the fraction.
Nope, you don't need the fraction here. That was my bad. That was my mistake.
Oh.
So I was ignoring the oxygen completely there.
Okay, makes sense. Thank you.
So if we were calculating the oxygen, I would have got the answer wrong for my test.
That was the test question.
Yep, that was the test question.
Okay.
Would have been out 20 points.
What was that?
We would have been out 20 points.
Yep, that's right. Because I screwed up my chemical equation. I'd have given you a few points.
Like a 0.5.
That would hurt even more. Just give me 0. Don't even give me 0.5.
Okay, piece of cake.